Hi, do you want to build a multimodal language model but do not have the data? Our method ASPER shows that reinforcement learning on its own is sufficient to align multimodal inputs to language models. As language models show remarkable reasoning capability, the next step will be extending them to multimodal inputs. However, the paired supervision dataset is often not enough. So we instead employ reinforcement learning. Here, we use clip model as a reward to measure the alignment strength between the image and the generated text. There are two benefits in doing so. First, one can use our method when there is actually no paired data, such as common sense graphs. Also, unlike supervised learning, our LL method maintains text diversity of the language model. Now, let's take a deeper look at our framework, beginning with the motivation. Why should one train a model without paired data? In specific domains such as knowledge graphs, social norms, or medical knowledge, even text-only data is scarce and hard to collect, let alone visually paired data. Here, we present a method to ground such data on visual signals. Secondly, and more generally, the paired caption dataset models only a narrow subset of possible text. Hence, models trained on them fail to generate text diverse in context and style, such as visual social media post, instruction, and story. Here, we propose ASPER to answer both the problems. ASPER connects a frozen GPT with a frozen clip using a lightweight encoder. Then, it first generates candidate captions to be rated by the clip. We use the clip outputs as rewards, iteratively train the model via reinforcement learning. Note that no paired data is required in this whole process, except for the off-the-shelf clip model. Maximum likelihood estimation is the go-to method to train image caption models. The supervised training process requires paired image text data. The paired data is then processed by the visual language model to yield the maximum likelihood estimation loss, which is backpropagated to update the model parameters. However, in our setup, no paired image text data is available. Instead, we have a reward model that can compute the strength of alignment between arbitrary image and text. So, on each step of reinforcement learning, we first generate the candidate image caption using the align policy of the visual language model. Then, the alignment reward is computed using both the image input and the generated text. The visual language model is trained to maximize the reward signal using proximal policy optimization, a widely used actor-critic algorithm. As stated before, we rely on CLIP, a contrastive estimator of image text alignment strength, as our reward model. Specifically, the respective CLIP features of the image and text are normalized and multiplied to calculate the cosine similarity score. As previous literature on applying RL to language models did, we use PPO, or proximal policy optimization. PPO requires three sets of parameters for the value model, the align policy, and the frozen reference policy. We share the architecture and initialize all three models with the same GPT-2, the language model. Finally, we use a set of auxiliary rewards to stabilize the training process, including K divergence between the policy and the reference policy, and the basic entropy of the reference policy, and finally, the static repetition score. There are two classes of language models we use in our experiments. On one hand, general language models aim to model the entire distribution of the natural language. We use the frozen GPT-2 here. On the other hand, domain-specific language models model narrower but deeper area of knowledge. We fine-tune the given GPT-2 in the respective domain-specific text-only data here. Let's turn to the experimental results. We first check whether our ASPER can actually build visually aligned text. Starting with the Cocoa captions dataset, we break the pairing between image and text to train ASPER. This trained ASPER model achieves strong visual alignment while staying much faster than decoding time algorithms such as ZeroCap or Magic. Then, we also check whether ASPER can align domain-specific knowledge as well. On the common sense knowledge dataset of Visual Common Sense Graph, ASPER shows close performance to the supervised baselines, even without seeing the paired image text data. In fact, ASPER is shown to be able to align a wide variety of domain-specific data, which are illustrated in our paper. It takes multiple diverse captions for a single image to accurately evaluate the controllability of an image captioner. Hence, we collect and release the ESP dataset. Our ESP dataset is manually annotated with text of multiple domains such as news, blog, and story for a single image. The dataset shares the images of Cocoa test set and further extends it with diverse captions. In the collected ESP dataset, our ASPER shows unmatched performance in each of visual relevance, informative, and fluency. Also, the performance of ASPER is stable across different domains, further demonstrating the text diversity of the method. As a final experiment, we also show that ASPER can incorporate auditory inputs as well. Using an audio version of a clip, waved clip in particular, ASPER generates audio captions without paired data. We evaluated in the audio caption dataset of audio caps and show that our method outperforms the baselines. However, the quality of generation in audio modality is lower than in visual modality. We attributed it to the reward model being relatively less trained, thus offering a noisier reward signal to ASPER. We released the code for ASPER and the ESP dataset in our website. Please take a look if you are interested in multimodal reinforcement learning or in need of an evaluation benchmark for your visual language model. Thank you for listening.